In mathematics, a measure-preserving dynamical system is an object of study in the abstract formulation of dynamical systems, and ergodic theory in particular. Definition: a measure-preserving dynamical system is defined as a probability space and a measure-preserving transformation on it. In more detail, it is a system with the following structure: is a set, is a sigma algebra over, is a probability measure, so that mu equals 1, and mu equals 0, is a measurable transformation which preserves the measure, i.e., this definition can be generalized to the case in which T is not a single transformation that is iterated to give the dynamics of the system, but instead is a monoid of transformations T's XX parametrized by Sz, where each transformation T satisfies the same requirements as T above. In particular, the transformations obey the rules, the identity function on X, whenever all the terms are well-defined. Whenever all the terms are well-defined, the earlier, simpler case fits into this framework by defining equals T's for Sn. The existence of invariant measures for certain maps and Markov processes is established by the Krylov-Bogolubov theorem. Examples include: mu could be the normalized angle measure d theta, 2 pi on the unit circle, and Ta rotation. See equidistribution theorem. The Bernoulli scheme. The interval exchange transformation. With the definition of an appropriate measure, a subshift of finite type. The base flow of a random dynamical system. Homomorphisms. The concept of a homomorphism and an isomorphism may be defined. Consider two dynamical systems and then a mapping as a homomorphism of dynamical systems if it satisfies the following three properties. The map phi is measurable. For each, one has. For mu almost all xx, one has phi equals s. The system is then called a factor of. The map phi is an isomorphism of dynamical systems if, in addition, there exists another mapping that is also a homomorphism, which satisfies for mu almost all xx, one has. For nu almost all yy, one has. Hence, one may form a category of dynamical systems and their homomorphisms. Generic points. A point xx is called a generic point if the orbit of the point is distributed uniformly according to the measure. Symbolic names and generators. Consider a dynamical system, and let Q equals Q1, Qk be a partition of x into k measurable pairwise disjoint pieces. Given a point xx, clearly x belongs to only one of the chi. Similarly, the iterated point Tnx can belong to only one of the parts as well. The symbolic name of x, with regards to the partition Q, is the sequence of integers, and such that the set of symbolic names with respect to a partition is called the symbolic dynamics of the dynamical system. A partition Q is called the generator or generating partition if mu almost every point x has a unique symbolic name. Operations on partitions. Given a partition Q equals Q1, Qk, and a dynamical system, we define T pullback of Q as further. Give on two partitions Q equals Q1, Qk, and R equals R1, room. We define their refinement as with these two constructs we may define refinement of an iterated pullback which plays crucial role in the construction of the measure-theoretic entropy of a dynamical system. Measure-theoretic entropy. The entropy of a partition Q is defined as the measure-theoretic entropy of a dynamical system with respect to a partition Q equals Q1, Qk is then defined as finally. The Kolmogorov-Sinai or metric or measure-theoretic entropy of a dynamical system is defined as where the supremum is taken over all finite, measurable partitions. A theorem of Yakov G. Sinai in 1959 shows that the supremum is actually obtained on partitions that are generators. Thus, for example, the entropy of the Bernoulli process is log 2, since almost every real number has a unique binary expansion. That is, one may partition the unit interval into the intervals 0, 1/2, and 1/2, 1. Every real number x is either less than 1/2 or not, and likewise so is the fractional part of 2nx. If the space X is compact and endowed with a topology, or is a metric space, then the topological entropy may also be defined. Examples: T. Sherman and I. Hoffman, the entropy of strange billiards inside n-simplexes. J. Phys. 828, page 5033 ff. 1995. PDF document.